Now I want to show you how you can use the Cardano CLI, the Cardano command line interface, to mint tokens having this policy that we just defined. And if you recall from lecture 3, where I demonstrated the use of the Cardano command line interface already, one of the things we need is the serialized script. So in the case of lecture 3, that was a validator, a Plutus validator, and now we have this minting policy. And if we check in the headoc documentation, minting policy is just a new type wrapper around the script. And if you recall, validator was also just a new type wrapper around the script. A different new type wrapper, but nevertheless, the representation is just a so-called script. So that means serialization is very similar, only that instead of having to first unwrap the validator constructor, now we must unwrap this minting policy constructor. I created a Haskell module called utils that contains lots of utility functions that we will need later, including this one, write minting policy. And this is very similar to what I did in lecture 3 for write validator, except now it handles minting policies. So the code is almost identical, but instead of a validator, it takes a minting policy. And in this composition pipeline of functions, the very first step here is get minting policy. So instead of unwrapping the validator to get to the script, we unwrap the minting policy to get to the script. And then the rest is the same. So as soon as we have our minting policy, we can use this function to serialize it to disk. So now recall we need 3 parameters. We need the UTXO, or rather a reference to that UTXO that we want to consume. And we need the token name and the amount. And then with these 3 pieces of information, we can use the function that we defined in the on-chain code, token policy, to calculate the policy. And then we can apply this function here, write minting policy, to serialize it and write it to our hard drive. Now, in principle, this is simple and straightforward. However, in practice, we must somehow get those 3 parameters, and in particular this UTXO ref. Let's have a brief look at the header documentation for this type, txOutRef. And it's just a record type with 2 fields, txid, transaction ID, and an integer. So the way it works is UTXO is specified by a reference to the transaction that created it in the first place. So that's this txid. And then an index. So each transaction has 1 or more outputs, and those are just numbered. So they are ordered. So the order of outputs of a transaction matters. Actually, the order of inputs does not matter, so that's unspecified. So it's a set of inputs, not a list, not an ordered thing. But the outputs must be ordered, so they have well-defined indices. And by specifying this combination of producing transaction and index, we can exactly specify which UTXO we're talking about. And if we just look at txid, this is just a new type wrapper around a built-in byte string, and a built-in byte string in turn is just a byte string, a new type wrapper around a byte string. And in particular, we see that txid implements isString. So if you recall, as I've explained several times before, in Haskell normally a string literal just represents a Haskell string, which is a list of characters. However, there are other string-like types in Haskell, for example text, which offers a more efficient implementation of textual data than string offers, or byte string. And if we want to use string literals for those, then there is this extension, this language extension that we have often used, overloaded strings, which enables us to use string literals to also specify instances of different types, not just string. Under the hood, the way it works is with this class isString. And isString has a method called fromString that goes from string to the type in question. So in particular, whenever we see that some type has an isString instance, then we could use a string literal in combination with the overloaded string extension to construct a value of this type, or programmatically we can use the fromString function to turn a string into this type. Maybe you're wondering why I explained this in so much detail. The reason is that we must get our txoutref from somewhere. So in particular, now that we're using the CLI, we must somehow get it from the CLI. And the CLI is a command line tool and works with strings, with the console. So we can query the UTXO sitting at an address, but then we just get some text. So we just see the transaction ID and this index. And now we must take that text and turn it into an actual value of type txoutref. So we must be able to basically pass a string into a txid, or more general, a string and an index into a txoutref. Now let's switch to the console, and I started a node, a Cardano node, and connected it to the testnet and had it synchronize. And how to do that I explained in lecture 3. And I also explained in lecture 3 how you can use the Cardano CLI to create a key pair. So I have this testnet folder. There's all sorts of config files and stuff in there, most of which you can ignore for now. But there is this node sock file, which is the socket that provides the interface from the node, and there are these files containing public keys and private keys and addresses. So I have actually two, so I have two key pairs. But now in this lecture I'm only going to use the first one. So 01.vkey contains the verification key, 01.skey contains the signing key, and 01.addr contains the corresponding address. So that's an address that, as payment information, uses this key pair, and that doesn't have staking information. Recall, an address in Cardano is this tuple consisting of the two parts, the payment credential and the staking credential. And the staking credential is optional. So if you don't have one, that just means that you are not delegating to any stake pool. And to keep things simple, I don't want to think about delegation now. So I'm just using a payment address that has no staking component. It's the same what I did in lecture 3. And I have this one file prepared. It's called query key1 shell. And that just uses the command I explained last time, the Cardano CLI query UTXO. And that takes two parameters, the testnet or mainnet that we're using. I'll come to that in a second. And then the address where we want to look up the UTXOs for. So to provide the address, I just use this file here, this 01.address. So as for the magic, I have another file prepared that I called env.shell, which just defines a couple of environment variables to make life simpler. And it also means that if you want to try this out yourself, all you have to do is edit this env.sh file. So the scripts should all be independent of the specific keys you are using, and once you set these things, then everything should be fine. So this Cardano node socket we need, so that's, as I said, it points to this node.sock file here. And we need the magic. So in the case of the mainnet, that would be minus minus mainnet. And in the case of the testnet, it's minus minus testnet magic, and then this number here. Address and wallet ID we'll use later when we talk about the PAB. So right now there is no wallet in play. Okay, and I can use this. So if I invoke this query, so I should say that in order for all of this to work, you have to source this file at some point. So in Linux, we do it like that. So now these environment variables are actually defined. So this is executed, and now I have these environment variables available. So I could, for example, say echo magic, and I get this value. Right, and now I can use this. So query key 1, and I see that I have a single UTXO sitting at the address given by this key pair. And it's just loveless, so there are no native tokens involved. So how much is that? It's 289 ADA, test ADA, of course. And this here gives the UTXO. So this is the TX ID, which is called TX hash here, and this is the index. And the way this is normally represented in the Cardano CLI is to take these two parts and separate them with a hash. So the corresponding UTXO would be this thing, and then hash, and then the index, which is 0 in this case. So in order to turn this into a value of type txoutref, I somehow need to pass an expression like this. And for that, I've also written a helper function somewhere here. The unsafe I've just used because something can go wrong, and then you would get an error. So it's not a total function. But if you provide sensible input, it should all be good. So what do I do? So the span function comes from data list, and it gets a list and then splits that list into two parts. The first part is consisting of all the list elements where this condition is true. And the second part is then the rest. So the first character or the first element of the list where the condition becomes false, and the rest. So in our case, we are dealing with strings, so a list of characters. This condition says not being the hash character. So when I do span, then the X will be all the characters before the hash, and then the Y and this thing will be the hash character and all the rest. So this underscore, I'm not interested in it because that will be the hash character, and the Y is then everything behind the hash character. Okay, so now I have these two pieces, and now I have to turn the X into a TX ID and the Y into an index, an integer. And as I explained before, because TX ID implements isString, I can use fromString applied to X to get the transaction ID. And in order to turn the Y into an integer, I can use read. So using this function, I can pass an expression like this. We can actually try it out in the REPL. So if I take this thing here and paste that in here as a string, then it works, and we indeed get something of type txoutref. And using this, I can write a little tool that allows me to actually serialize the correct minting policy. So this is an executable. It's actually called token policy. It's defined in the Cabal file for this project. And what I do is first I get the command line arguments. So I expect 4. It's done by the standard Haskell function getArgs. So the first one is the file where I want to write the serialized minting policy to. Second one is the UTXO reference that we have been talking about now. Then the amount, how many tokens do I want to mint, and the token name. So first I have to pass these 4 strings, they are all strings, into the correct types. So for the WoRef, the reference to the UTXO, I use this unsafe read txoutref that I just explained. For the amount, I can simply use read. For the token name, I can use fromString because token name also implements the isString class, similar to TXID. And once I have these pieces, I can apply my token policy function that I showed earlier. Now I have the 3 necessary arguments for that to get the actual minting policy. And then I can use the write minting policy function to write the serialized version of this minting policy to the file named file. We can actually try this out. So I can execute this tool with cabal run or cabal exec. So it's called token policy. And now in order to pass in command line parameters, when I use cabal exec or cabal run, I first need a double dash, and now I can list my parameters. So the first one was the file name. So for example, we can use policy.plutus. Now the oref, so that's this thing. Now the amount and the token name. So let's say I want to mint 1, 2, 3, 4, 5, 6 and token name PPP for Plutus Pioneer Program. Okay, so something happened. And now if I look at this policy.plutus file, I do indeed get the serialized version of a Plutus script. So that's the first part that we need in order to use the Cardano CLI to mint tokens of this type. I need the policy script in serialized form. So that we now have. Luckily, this was the hardest part. So now we can actually do the minting using the CLI. And for that, I prepared a script called mint token CLI. And it expects 5 command line parameters. The first is the UTXO reference that we also now just use to compute the minting policy. Second is the amount. Third is the token name. Then the name of the file containing the address, my own address. So that's used as a change address because obviously we are not going to spend all these 90 ADA. We just have to pay some transaction fees. So there's lots of change. So that goes back to this address. And the freshly minted tokens also will go to this address. And finally, the name of the file containing the signing key, because I need to sign the transaction. So I just log some information, log these parameters. Then I need the so-called protocol parameters. And in order to get them, there's another command, subcommand of the Cardano CLI. It's called query protocol parameters. It takes the magic and it takes an out file parameter to specify where to write these protocol parameters. So I write them to testnet/protocol parameters.json. So it's a file in JSON format. Okay. Then I have to do what I just demonstrated by hand. I need the token policy. So I use this little tool that I wrote, the token policy tool, and invoke it as I just showed you. So as file name, I use testnet/token.plutus. And then these 3 parameters I have from the parameters to this script here. Okay, so at this point now the policy should be in this file. Now I need the policy ID, which is basically the hash of the policy. It's also the sort of the currency symbol of the token. It's different types. One is policy ID, one is currency symbol, but underlying representation, the underlying byte string is just the hash of the script. So I could use Plutus and Haskell to compute that, but I can also use the Cardano CLI. So the Cardano CLI is a subcommand transaction and then a subcommand policy ID. And as argument, it just takes the script file and then it returns the policy ID. So we now have our policy file. We wrote that in this step. So now I can use this Cardano CLI command to get the actual policy ID, and I assign it to this variable PID. Now there is one further complication. I want to mint a token in this example with token name PPP. But the Cardano CLI, since recently, doesn't understand these plain text token names any longer. It insists that all the token names are in hexadecimal. So we somehow have to convert this PPP to the correct hexadecimal representation. So in my utils module, I wrote a function for that. So it takes a token name, returns a string, and does just that. And it's yeah, again a composition of lots of little functions. So first I have to unwrap the token name. So token name is just a new type wrapper around a built-in byte string. So now I have a built-in byte string. A built-in byte string is just a byte string, a new type wrapper around a byte string. So with get byte string, which I define here, I get to that. Then I use a function from the Cardano API, which is the Haskell library that provides all the functionality that the Cardano CLI uses under the hood, to deserialize that into a so-called asset name. So asset name is the Cardano API type that corresponds to the Plutus token name type. So in the Cardano API it's called asset name. So at this point I have an asset name. This deserialize returns a maybe type because deserialization can go wrong, but I ignore this, so I insist on it going right. So if it doesn't, then at this point we would get an error. So I use from just to turn this maybe asset name into an actual asset name. And then I use another function from the Cardano API, serialize raw bytes hex, to turn this into a hexadecimal byte string. And finally, I turn the byte string into a string because I just want a string. And I also wrote a little tool to use this. That's called token name. And it just expects one argument, the token name, and then it passes this token name, prime the string into an actual token name, and then uses the function we just looked at, unsafe token name to hex, to produce the corresponding hexadecimal string. So we can try this out as well. So I can say cabal exec token name, and it takes the token name. So if we use PPP as an example, then we see the corresponding token name that the Cardano CLI understands is 505050. Going back to our script, I use this tool token name to do just this, to convert the token name that the user provides here as an argument and assign the result to a variable tn hex. Then address, I just read from the provided file name for the address. And now the v is the value that I want to mint. And the representation that the Cardano CLI uses for these things is first the amount, then a space, and then you specify the asset class by first giving the policy ID, then a dot, and then the token name. And that must be this hexadecimal token name. So this v is now the amount I want to mint. So in our example, that would be 1, 2, 3, 4, 5, 6 space, then the policy ID, whatever it is, and then dot 505050. So I just log some information, and now comes the main thing, the transaction build command of the Cardano CLI. And it's actually, after all the work we've done before, relatively short. So it takes the magic, then inputs can be specified with txin. So in this case, because it's just a public key input, it's simple. So I don't have to give redeemer or anything. So that's just our oref. Now collateral. I am not sure whether we have spoken about collateral before. So validation at a node, transaction validation, happens in two phases. So the first phase is quick and cheap, and it checks things like that all the inputs are still available, haven't been spent by a different transaction, and that the validity interval is correct. So it checks the current time against the validity interval in the transaction and checks like that. And in the second phase, if the first phase goes well, the scripts are run, if there are any. So all the validator scripts for script inputs and all the minting policies for minted tokens. And this second step should never go wrong, because if you, for example, use the Cardano CLI or the PAB and you have a transaction that's invalid due to a script failure, then you can't submit it in the first place. So whenever a node gets to the second phase, that second phase should always succeed. Which also means that on Cardano, you never have to pay for failing transactions, which is different to, for example, Ethereum. There it can happen that you have to pay gas fees and then eventually your transaction fails. Cardano, that can't happen, except if you try really hard. So you can circumvent the mechanisms and basically force an invalid transaction to be spread through the network. And then only in this case, this second phase would fail. But this second phase needs some effort from the nodes because they have to run the scripts. So that takes time and resources. So that would be, if it was for free, if there was no punishment associated with that, it would be a potential attack vector against the network. It would be a DDoS attack. If people could, for free, send invalid transactions and keep the nodes occupied by running these failing scripts, then that would slow down the network. So therefore, there's this collateral mechanism, which says that every transaction which contains scripts, could be validator scripts, could be minting scripts, could be something else, need to specify so-called collateral. And collateral must be a pub key input, and it must only contain ADA, so no other native tokens. And then the rule is that normally nothing will happen. I mean, if you just use the normal tools, the Cardano node, the PAB, whatever, then the second phase will never fail and the collateral is ignored. But if you do something fishy and circumvent these protections and have an invalid transaction, so the second phase of validation fails, then the collateral is forfeit. So you lose the collateral. So that means in our case, because we have a minting policy that must run, we need to specify collateral. And we can simply use the same OREF, the same UTXO that we also use as input, because that fulfills the criteria. It is a public key input and it only contains ADA. Then we specify an output. Normally that wouldn't be necessary because the balancing would take care of that and just create a change output. However, change outputs only work in this version of the CLI for ADA, not for native tokens. So I explicitly create one. And the syntax for that is, as I probably explained last time already, address and then plus the value. So address is the address we specified earlier, so our own address. And this is the value we want to mint. But there's also this thing of min ADA, so each UTXO has to contain a minimal amount of ADA on top of any native tokens. And this is a bit lower than 1.5 ADA, but I just wanted to keep it simple. I am not exactly sure how that's calculated. I think it also depends on the size of this output, the size in byte. So it's not a constant. But 1.5 ADA should be enough. Then this is the most interesting part. This mint argument says how much the transaction should mint, and that's exactly this V value. Mint expects the script file, so we worked very hard to get that. So now we have it here. And mint expects a redeemer file. So the redeemer recall for this minting policy was just unit. So we need unit represented as JSON. And we also needed that in the example of lecture 3. So basically I just took the file that we got in lecture 3 and copied it to lecture 6. We must specify the change address, which is again our address. Now we need the protocol parameters. That's why earlier I had to work to actually get them. And I must say where to write the transaction to. So this is an unsigned transaction. It will be balanced, but it won't be signed yet. And then as before, I need to sign and submit. So in order to sign, I have to specify where to find the unsigned one that I just got in the previous step. I must specify a file containing the signing key, again the network magic, and a file where to write the signed file to. And then finally submission, again I need the network magic and the signed file. And that's it. Now I can try it. So let me run query key 1 again so that I see the UTXO again. Okay. And now I can run my script, min token CLI. So first parameter is the UTXO I want to spend. So that's as before this and then hash the 0 here. Now the amount I want to mint. So we wanted to use 1, 2, 3, 4, 5, 6. Now the token name, we wanted to use PPP for Plutus Pioneer Program. Now the address file, so that's testnet01 address. And finally the file containing the signing key, so that was testnet01 skey. And if all goes well, if I press enter, this should mint 1, 2, 3, 4, 5, 6 of these tokens with token name PPP, which will be displayed by the CLI as 505050, but certain wallets, for example your Roy wallet, would display it as PPP. So this looks promising. There was no error. So we see the various log information here. So for example, we see that the currency symbol or the policy ID will be this token name, and here we see it costs us 343,733 loveless in transaction fees, and that the transaction was successfully submitted. So now I have to wait for the next block, which on average takes 20 seconds, but of course it can be shorter or it can take longer. And then I can query key 1 again. So let's do this now. So it's still the same, which means the next block hasn't been created yet. So I just have to be patient and try again after a couple of seconds. And there we are. So now we see we have two UTXOs. So this is now a different one to that one. So it's completely different because we now have this minting transaction, and this here must be the transaction ID of the transaction we just created and submitted here. And that has two outputs. So this is the change output. So that's the ADA I didn't need for fees or for this min ADA here. And this is the one we worked very hard for to get. So it contains the 1.5 ADA min ADA, but, and that was the whole point, newly minted token. So we indeed have 1, 2, 3, 4, 5, 6 amount, and then this currency symbol, which we saw here, and our token name. So it worked. We successfully used the Cardano CLI to mint a native token. To prove that this is for real and really happened, we can check the Cardano Blockchain Explorer for the testnet, and I copied the transaction ID we saw, and let's see. And we indeed find the transaction, and we see that as output it has these two outputs, 287 ADA, that's the change output, and then this one with the 1.5 ADA min ADA, and in particular these 1, 2, 3, 4, 5, 6 here. And if we hover over this, then we see the information. So we really minted our tokens on the Cardano testnet. And of course doing it on mainnet would be exactly the same. The only difference would be the magic. It would be minus minus mainnet instead of minus minus testnet magic, this cryptic number. And obviously we would have to pay real money to make it happen. Real transaction fees, real ADA.